Please.
Okay. Yeah. Hello, everyone. So today we are starting with Solidity. Finally, I would like to talk about Solidity type system, how variables work, what types of variables there are, what differences between, for example, storage variables, memory variables, and how this works on EVM level. If you have any questions, just type them in chat and I will quickly answer to them. Yeah, so let's start. On the previous lecture, we have touched briefly Solidity. So you remember that Solidity is a high-level programming language that is used to write smart contracts on Ethereum blockchain. Solidity is basically a compiler that reads your high-level code and translates it to some bytecode. And Solidity works in a special environment called the Ethereum virtual machine that has a lot of places where it can store variables, for example, and where the bytecode of the smart contract is interpreted, and etc., etc. So Solidity has to somehow work with that EVM environment, and the compiler has to interpret whatever you wrote in the high-level language to the bytecode. So there are 4 different Solidity variable types that that you can, for example, allocate, that you can use. So the first one is the value types. It is the most simple type that you can operate with. We'll talk about them on the next slide. So these variables live on stack and are used, for example, inside the functions. Then number 2, memory types. These are special types variables that consume more memory than stack allows, so they have to be placed somewhere else, so outside the stack. These variables live in memory, and you can think of memory as the heap from traditional programming languages. And Solidity keeps track of those allocated memory variables by storing pointers to them on stack. And number 3, a special user-defined types that also mostly live in memory and also have stack pointers. But for example, they can aggregate several other value types or memory types. And number 4, there are type aliases, which are just compiler abstractions. So these type aliases were introduced in new versions of Solidity. So yeah, in future releases, actually Solidity developers will be allowed to use more aliasing. And for example, in Solidity version 8.19, the overload of operators was introduced, and yeah, Solidity core developers will expand the capabilities of this type aliasing for the future releases. So yeah, we'll talk about this as well. So talking about value types, there are not so many of them. The first one, the simplest, is Boolean, which can only hold false or true. And for example, when you're constructing the data, the ABI encoding Boolean value is substituted with uint8 value. So for example, if your function accepts a Boolean parameter, then in the ABI encoding, instead of Boolean, the uint8 will be used. Actually, I won't talk about basic stuff that you can get just from reading the documentation. So here I will explain something different, something more complex than just what you will get from scrolling the official documentation. Then draw signed integer types. This number here stands for the bit count of the integer, and the maximal bit count is 256. What is cool about integers, signed integers, that they are represented in the following way. So this, the leftmost bit of the integer, you can think of it as a negative bit. So when it is set, then the EVM will interpret this value to minus 2 to the power of 255. Oh, 256 minus 1, yeah. And every other bit that is set, the value of the number will be added to this negative big number. So in the end, if every bit is set, you will get -1. So the leftmost bit represents the most negative number that is possible to represent, and every other bit to the right represents the positive number, which are then added. And if all the bits are set, you will get the -1. So signed integers are represented like this in Solidity, and actually in, for example, C++ as well. Then there are unsigned integers, which are also the maximal value of unsigned integer is 2 to the power of 156 minus 1. And yeah, they are just regular numbers where, nothing special here. Just the rightmost bit is 2 to the power of 0, then 2 to the power of 1, and everything is added. So you get the answer here. Yeah, so just like that. Also, there are special types called address and address payable. So these are the representation of contract addresses and external account addresses. And the difference between those two is that you can't send Ether to the to the address with the type address. So you will have to cast this address to the payable one in order to send Ether. And then draw bytes. Here the number on the right represents not the bit count, but the bytes count. So here we have 256 bits, which is 32 bytes. Here we have 32 bytes as well. What is cool is that bytes are, bytes are represented from left to right, not from right to left as our regular numbers, but from left to right. So the value 3 would be here if we set 2 ones on the leftmost part of the bitwise representation. But value 3 in our integer representation is the 2 rightmost bits which are set to 1. So basically those values are sort of mirrored. Yeah. Address is represented in a like bitwise form, the same way the unsigned integers are. So the address will be placed or will be started from the rightmost bits, not from the leftmost ones as the bytes. So here is a quick example of the types that I talked about. For example, bytes 4, just regular variable, which lives on stack because it is allocated inside the function body, and it is assigned to the function selector. We'll talk about functions in the upcoming lecture, and also I will cover what selectors are, how they are constructed. But for now, it is just the like function signature. It is a value that represents this function, and it is encoded as 4 bytes. So bytes 4. Here is the variable of the type address, which is assigned to message sender. Then we have variable of type uint 256, which here I cast the caller of type address to uint 256 by first casting the address to uint 160, because address is 20 bytes long. So this rightmost 20 bytes can be cast to the integer representation, which is also 20 bytes here. And after that, this can be cast to the bigger integer without like changing the actual value of the caller. So here it is. And Boolean value, which is assigned to this expression, and this expression is true due to the bitwise representation of numbers. So here we have the -1 of type int 256, and I compare it to the negation of bits of 0 number representation, also of type int 256. And from the previous slide, remember that if all bits are ticked, then it's -1. So here is the proof that it is exactly as it is. Okay. So memory types. We have 4 memory types, like 4 groups of memory types in Solidity. The first one is bytes type, which is basically like 4 bytes that are tightly packed into a complete like string or a complete sentence of bytes. Also, there is a string type, which is used to represent strings. And in Solidity, they are like every symbol of the string is encoded in the UTF-8 encoding, which might be 1 byte long if it is an ASCII symbol, or it can be like up to 4 bytes long if there's some emoji or something like that. But still, Solidity can understand emojis, so you can, for example, if your function accepts strings, you can send emojis there and display them on your front end, for example. Yeah, and those strings can be easily cast to bytes, but yeah, their lengths may vary if any symbol in the string is more than 1 byte long. Then there are fixed length arrays and dynamic length arrays, which may be like multi-dimensional arrays. So, for example, we are not limited to a single dimension. We can have like an array of arrays of arrays, and etc. etc. Actually, I think the most, like the deepmost inclusion of arrays is like 16, because more than that, like Solidity doesn't allow more arrays than that due to the EVM limitation, because you can't read the variable like lower than or deeper than 16 elements from like the top of the stack. Yeah, what does tightly packed exactly mean? I will return to that in upcoming slides. So I'll answer that question. Yeah, so here is an example of memory types. So here is like an allocation of memory type, which is of type bytes, and we just assign the value of this like raw byte representation to the variable. So this basically means actually nothing, just some random bytes. Here is how you allocate the string variable, just like that. Here is how you allocate the array, also pretty simple. Here is the array, the static array of length of 2. Here is how you allocate that. And here is the array which contains arrays inside. So here is a catch. So this is the dynamic array of static array of strings. So Solidity interprets that is the like closest braces are the ones that are like more inlined. Yeah. So this 2 is the inner array, and this like empty braces are the outmost array. And this notation is actually reversed, for example, to C++, where in C++ this would mean like an opposite thing, but here it means the dynamic array of static arrays. But the access to this array is the same as in C++. Yeah, here is an example of user-defined type. So here is the struct, which I named user, which has 3 variables inside. The name variable of type string, the account variable of type address, and the age variable of type uint32. And here is the function, how to construct, how to assign value to this user-defined type. So just like that, or you can use the dot notation. So for example, to assign account value, you could just type user.account equals message sender. But here is the more fancy way to do it. And about type alias, here is a tricky example of this aliasing. So it is normal Solidity as it is. So we have a type myuint, which is the alias type of uint256. And here we have a special contract, which is also a Solidity feature, because it is not like a regular contract, it's a library contract, but we will also cover libraries in the future lectures, but just bear with me right now. This function accepts our alias types, and alias types have two like built-in functions, the unwrap function and wrap function. So what it basically does is that the myuint.unwrap a, it just takes our custom type and interprets this as a type we aliased. So this is basically means cast my type to type uint 256. Then take B, cast to uint 256, add them up using like a regular addition of two numbers, and then cast it back to my type and return it. Yeah, so hope this is clear. So here is the question. There are many types in Solidity, but there is no type for fixed point numbers. So there are no floats, no doubles, yet, at least. There is a discussion to actually like long-lasting discussion, which started from the beginnings of Solidity and is still ongoing. So there are plans to add fixed point numbers to Solidity, but what to do now? So Solidity doesn't support fixed point numbers, and we have to overcome this limitation with some trickery. So the trickery used is if, for example, you need to calculate this expression, so if you need to divide 2 by 100, what to do? You just multiply this expression by some kind of fixed precision. Usually precision is used rather large. For example, like 10 to the power of 18 or 10 to the power of 25. And once you multiplied like your number you want to divide, you'll receive a huge number. So dividing this huge number by 100 wouldn't result into like zero, wouldn't result into zero. So it would still be a huge number. And then you would keep this huge number on your smart contract. And when the actual result is needed, your front end or service will just query the contract, receive this huge number, and divide it by the precision you use on the smart contract. And because the offchain services like use fixed point numbers, so after their division, they will receive the regular number that would be displayed on the front end. So basically, there are actually a lot of like contracts out there, a lot of open source libraries that somehow optimize this process. For instance, instead of using the multiplier, like instead of multiplying the number, you can offset the bits of this number to the higher orders. And this is cheaper. So once you offset the bits, you're like will be working with a bigger number. So no worries of precision loss there. So you will do everything. Once your like result is needed, then the service would query and shift the bits back to whatever position they have to be. So yeah. So we talked about just like types, the type system Solidity uses, but where can you allocate those types? Where can you use the variables of those types? So actually, there are 5 main locations where Solidity keeps like variables, where you can allocate those variables. First one are local variables that live on stack. These are the ones that you use in the functions. Then there are memory variables, pull data and return data variables. So this is actually read-only and like managed by EVM. So there are no like direct way of writing into those locations, but there are opcodes that somehow like manage those data locations, but it is all done inside the EVM. Then there is storage and constants with immutables. So let's just quickly understand what those words mean by like understanding what are those locations in the first place. So storage, it is a special data location where smart contracts store their variables and store their state. So this is the these are variables that are used in a global scope of the contract. We'll have an example after each definition. So just bear with me a bit. And how storage works. So basically, it is the map. So the key is the 32-byte number, and the value is the value that is like stored under this key. And if you want to write anything into the storage, you have to understand under which key or which slot you're writing. And Solidity like manages this writing because it understands what is written in your like, high-level language. So when you allocate or use a variable in your like global scope, it understands that this variable is put on slot, for example, 2. So when you access it, you will actually be reading the value that is stored under slot 2. And if you are using something more complex, there are ways of understanding where the data or where the value of this complex variable, for example, the array or your struct, where the data of this variable is stored. So I will show you an example. It will be a bit more clear. What is different, like what differentiates storage from anything else is that the storage is retained past the completion of the transaction. So if you write anything into storage, it will stay there until you like clear this slot. So it is permanent. Yeah. If Ethereum works, then whatever is written into the storage stays there permanently. And storage is like non-initialized storage is the one which haven't been written into. So here on this diagram, for example, we have written something into the slot 0, but slot number 3 is untouched. You still can access this slot, but it will just return the 0 value, so 032 bytes. But yeah, you still can do it. The memory. So memory is a bit different from storage, and smart contracts use memory as some kind of temporary data location. Memory is cleared every time you're calling a contract. So, for example, when you're initially sending a transaction, you'll be calling some smart contract. So the memory will be zeroed for this call. If your smart contract calls another contract, there for that second contract, the memory will be also cleaned, and this second contract will access it normally. When the call is finished and you return to the first contract, your memory that you left before calling the second contract will still be accessible. So it is just it is allocated every time you're calling something new, and when you're returning from this call, the memory is cleared. Solidity right now doesn't have some fancy memory management. There are no constructors, destructors. There are no garbage collectors or something. It is pretty simple, but there are several special memory slots that Solidity uses to actually work. So first of all, memory starts from the 0 slot, and you can see that those 2 first slots Solidity reserves for scratch space. So it stores some temporary data that will be overridden every time when it is needed. So it can store some, I don't know, hashing results or anything it wants to store really quickly and temporarily. It will be doing it here. Then starting from memory address, so memory pointer in hexadecimal representation 40, the third slot of the memory is the 3 memory pointer, which Solidity initially sets to point to the pointer. So this slot contains the pointer to the next free memory location, which you can use to allocate, for example, dynamic arrays. And Solidity uses this slot to indicate what is the next chunk of free memory available, and if it allocates some memory here, it also updates the free memory pointer here to point to the new free location. And actually, memory in Solidity never decreases, so it can only stay the same or increase. So this pointer will either stay the same or rise. Yeah. And starting from the pointer 80, the empty. Oh yeah, I also missed the 0 slot. Yeah, this is also something Solidity reserves for arbitrary something. So it can store some random variables here, which should also be ignored. They are fully managed by the compiler. so compiler knows what's written there and how to interpret that. And starting from pointer 80, we have a free memory accessible to everyone. And this access is allowed up to slot number 2 to the power of 156 minus 1. So you can access a lot of memory, but Solidity has a constraint that with each memory slot accessed, it takes some gas. So accessing new memory requires payment. And the payment function is quadratical. So accessing slot number 10 costs n gas, but accessing slot number like 100 costs how much? 100 n gas. So it is like quadratical. So at some point you will just run out of gas and that's it. And third type of variables that you have to understand before the example is the constants and immutables. So Solidity has this special variable that you can also allocate either during compilation. So constants are allocated during compilation and usually also evaluated during compilation, and then placed in the bytecode directly where they are used in the functions. And immutables are like sort of the same, but instead of evaluation during compilation, they are evaluated during contracts deployment. So when the constructor is run. And then they are also placed in like directly in the bytecode where they are read from the functions. So yeah, just let's hop onto example. Here we have contract example, and there are two variables here. The first one is a constant variable that you have to assign to something just like that. And this, so I named it admin. This admin will be like I assign address 5 to this variable, and also in the function set name, we have this variable used. So what's going to happen? During compilation, Solidity would understand that it is the constant variable. It would try to evaluate what is written here. Sometimes it is successful, sometimes it is not. So here it is successful because it is a simple expression. And this simple expression will be placed directly here, like into the bytecode where this comparison is made. So what I mean by sometimes it is successful, sometimes it is not, you can assign really complex expressions here, like address 5 casted to uint 160, then casted to uint 156, then add 1, then subtract like 1, then add something else. So this expression Solidity is unable to evaluate its compilation. So instead of the actual value, it will put into the places where this constant is used, the actual expression that you wrote here. So not the value of this expression, but the actual expression. And yeah, this is just what you need to understand. Then there is an immutable variable. I named it self because in the constructor, the self is assigned to address this. So basically, this immutable variable has has a value of address this, so of the address of this smart contract. Immutable variables are evaluated during constructor and also placed directly into the bytecode wherever they used. So here it is unused, but it will be like the actual value of this variable can be seen if you inspect the bytecode of the contract. Yeah, then there is a storage variable. It is not named. So it is like neither constant nor immutable. And here is what indicates that it is a storage variable. First of all, it is accessible in the global scope of the contract, and it has none of those names. So it is a storage variable. And here we have a function that accepts a string in call data location. So external functions and public functions are allowed to read the call data. It is like the actual data that you passed in the transaction data field. And Solidity understands that somewhere there, the string variable is encoded. So you can say that we will be using this data directly by saying that this string is from the call data location. So it is just cheaper than using, for example, memory. Yeah, and here our like business logic line, we are setting the name, which is this one, to the name which we passed in the function. And let's talk a bit how this name is laid in the storage, because it is not that simple. So every variable that is declared in the global scope of the contract, Solidity understands under which slot it is declared. So here it is the first variable to be in the global scope, first storage variable. So it is declared on top of the slot 0. But strings, bytes, static arrays, and dynamic arrays, they are encoded with the length as like not the first element, but pre-first element. So sort of minus first element is the length. So under slot number 0, you will observe the length of this string variable. And depending on the value of the string, either the value of the string will be placed in this slot. So you take the slot of this variable, which is 0, hand it to the catch-256 hash function, get the result of this hash function. So there will be some random, like not random, but huge number. And this huge number is used as a slot where the value, where the actual data of this string is going to be placed. And talking about strings, this will be used only if the length of the string is more than 31 bytes. But if it is not, if it is less than 31 bytes, then the actual data, the actual value will be also encoded or tightly packed into this slot. So you will have the length in the lowest bits of the slot, and then the actual value, the actual data in the highest bits of the slot, or the topmost bits of the slot. And Solidity all does it for you, so to pay less gas for storage. That is all needed because Solidity, or not Solidity, but EVM charges 20,000 gas for every new slot that you allocate, but every 5,000 gas for the slot that you change the value of, if it is already allocated. So writing data to 2 slots will cost you 40,000 gas, but writing only to 1 slot, only 20. So if the string is short, it can be tightly packed into the slot to take only 1 slot, but not 2. So this is cheaper, and Solidity does it for you, so to be cheaper to run, so you don't have to think about it. And what actually happens here? So we have a variable in the call data, but we assign it to the storage variable. So what happens here is we take the variable from call data with special opcode, we place it in the memory, the one like we discussed, and then Solidity takes this memory and through the special opcode places whatever is placed in the memory to the storage. And yeah, basically in this equation, we have 2 tasks that Solidity does. First one is take value from call data loaded to memory. The second one is take whatever is loaded to memory, place it into the storage. Yeah, hope this is clear. I have to move on. Curious what I mentioned about the tightly packing of storage. So here we have 2 structs, which only differ in the types. So every slot, the storage slot, is 32 bytes long. And if we have 2 variables that allocate 32 bytes each, then we will be using 2 slots to save this struct to storage. If your business logic allows to shrink the type of the variable, so for example, number of students, it surely can't exceed the unit 128 because it is just a massive number. There are less, actually not less, but not significantly more particles in the universe than this number. So it's impossible that there will be more students than this type allows until it overflows, yeah? So here we pack those 2 variables into 1 slot. So when we'll be saving this struct to storage, it will only consume 1 slot, so it is cheaper. This one is not optimized. It will consume 2 slots, just more expensive and not so conventional. Yes, and what is important is that this is only related to storage. Memory doesn't work this way. Memory works a bit differently. So in memory, it will allocate 32 bytes per variable. Doesn't matter which type it is. It can be Boolean. It can be like uint 64. It can be uint 256. Doesn't matter. Each variable will consume 32 bytes of memory. Always. This is related to Solidity. So probably other programming languages might optimize this, but Solidity doesn't. This is how ABI encoding works. And Solidity tries to follow the standard actually that was developed for Solidity. But for example, other smart contract languages might not follow ABI encoding and use something else, something more efficient, whatever, if they understand how to encode and decode it efficiently. So Solidity uses ABI encoding, and in ABI encoding, every variable uses 32 bytes of memory. Yeah, so this is just the way it is. But what is even more important is that premature optimization is the root of all evil. So it is really easy to be trapped in this optimization stuff. And instead of writing valuable code that you have to deliver to some customers, to the clients, to your manager who is waiting for the code to be written, you can just be distracted to think of how to write this code better. But this is actually doesn't speed you up. It is just a waste of time. So in Solidity, it is really, really easy to be trapped into this, because there are a lot of ways how to optimize code, how to make it more efficient gas-wise, how to make it more efficient byte code-wise. But please, first of all, write code that will work, and then try to optimize it. Just never optimize it before writing, unless you are understanding that it is the only way of doing it. Yeah, actually, that's it for today. I've just checked the questions. Are there any tools that help automatically optimize the cost of the smart contract in the development process? Yes. So Solidity compiler has a special flag that you can use to optimize the code. It does everything for you. It is not optimal at all, but it does optimize something. So this flag, its name is optimizer, and the value of the optimizer, so usually it is set to 200, but what this value actually means is how many interactions with this smart contract is expected during the lifetime of this smart contract. So, for example, if you place this value to 1, the optimizer would try to optimize the code in a way that will be byte code wise the smallest, but it will be really expensive to call the functions. But if you place the value to some huge number, for example, to 10,000, yeah, then the byte code will be huge, but the cost of calling functions a lot cheaper. Slides you said that in Solidity now fixed point values, but actually I understand there's no. Yeah, so those terms are like interchanged. So in their documentation, they use it interchangeably. So they actually call it fixed point values, but yeah, these are floating point values. You will actually find that you can declare those values, but you're not allowed to use them. And yeah, but this basically means that Solidity doesn't support them right now. Yeah, actually, there is a lot to talk about, like more deep or deeply how, for example, different types are represented in the storage, how mappings work in storage, how ABI encoding works, how memory works, how different opcodes behave. But I will try to like quickly cover those things in the upcoming lectures when I will be discussing functions and other niceties of EVM. But yeah, EVM is really huge and basically it's impossible to like pack everything into one course. So yeah, and these are pretty advanced topics. So yeah, I don't know, maybe we'll be doing another like advanced Solidity course in the future sometime. What does this mean? What does passing 5 to address mean? Would be by the representation of 5. So basically this means that it is address with number 5, which is all zeros from the right to left. And like at the left, the 5 will be used. So it's just like writing the address with the 5 as the rightmost number. So basically it is the value of the rightmost byte. Yeah, also in future, I'll talk about the gas cost of constants, immutables, and storage variables. But as a rule of thumb, you can like take for granted that constants and immutables are a way of optimizing smart contracts. So instead of using storage variables, you can use constants or immutables, and this will be much cheaper for users to interact with the smart contract. But yeah, optimization is like a completely different topic of research, and there are so many ways how to potentially optimize the smart contract that yeah, probably someone can write a book about how to optimize smart contracts. Yeah, but remember, don't think that information optimization is the root of evil. it is crucial. Okay, so Lena, are you here?
Yeah, I'm here. I'm sorry. What about home task? I'm so sorry. Please repeat if you don't say about this. Artem? What about home task? Please repeat if you don't say about this.
Oh yeah, about the home task. Yeah, so the practical task will be available after the lecture, probably like in an hour. You will have to do a like not so complex task for the first Solidity practical task, and there will be a document with the specification with the explanation of the task provided. So basically, you'll have to write a contract, deploy the contract, and call several functions on the validator contract. So this validator will check if you have completed the task successfully.
Mm-hmm. Okay. After this lecture, I will add the presentation to the classroom, and maybe tomorrow we will add the home task. Yeah.
So I will send it like in an hour. So whenever you like. So today, tomorrow.
Okay. And if all questions have been answered, we can stop. Yes.
Yep.
Thank you for a lot, Artem. Thank you for a lot, all our students, and see you soon. We will be wait for your answer for our task. Thank you.
Yeah, bye.